Okay, so we're going to finish up our chapter on applications of aqueous equilibria, and we're going to move on to part 3. So we talked about acids and bases and titrations, and then we talked about ions and solubility and precipitates, and now we're going to look at complex ions. Alright, so a complex ion is a charged species consisting of a metal ion surrounded by what are called ligands. And a ligand is a Lewis base, so it's a molecular ion having one lone electron pair that can be donated to an empty orbital in the metal ion, thus forming a covalent bond. Some examples are water, NH3, the Cl- ion, and the cyanide ion. When we look at these complex ions, we also have what are called coordination numbers, and these are the number of ligands that are attached to the metal ion. So some common ones, a coordination number of 6 could be something like, let me get a pen here, cobalt and 6 waters, and so that 6 corresponds to the number of ligands attached to the metal. If you have a coordination number of 4, then you could have like 4 chlorine ions, and a coordination number of 2 might be 2 ammoniums. And you can also see they're all charged species with a metal and this ligand. Okay, well, we also have what are called formation constants or stability constants. And these are basically equilibrium constants that characterize the step-by-step addition of these complex ions. It's kind of like when we talked about polyprotic acids where we removed one acid at a time. Kind of the same thing, only we're adding a complex ion each time. So for example, for a mixture of silver and ammonia, we can add one ammonia complex ion to form AgNH3+, and that gives us a K value of 2.1 times 10 to the third. Notice that all of these are very large. Okay? So then we can take that product and make it our reactant, add another complex ion, and maybe it becomes AgNH3+, and our K2 value is 8.2 times 10 to the negative 3. Or sorry, positive 3. So I used to say negative. So in this case, all species will exist at equilibrium, and sometimes calculating the concentrations of all of our species can be complicated. And so the total concentration of the ligand, which in this case would be NH3, is usually much higher than the concentration of the metal ion, and so we can make some approximations to calculate concentrations. Kind of like how we assumed that the X value was always so small. It's kind of the same thing. So let's look at an example. I want to calculate the concentrations of silver, AgS2O3- and AgS2O3-3- in a solution. So we're going to have 150 milliliters of 1 times 10 to the negative 3 molar silver nitrate, silver 1 nitrate, and 200 milliliters of 5 molar Na2S2O3. And so if we look at the steps for the equilibrium, we have silver plus the S2O3 2- forming AgS2O3-. So we have one complex ion, and we have the K value for that. And then we take that and we add another complex ion, and so we form AgS2O3-, and we also have the K value for that. Okay, well, just like we've done before, let's look at the concentration before the reaction. So if we want to calculate the concentration of just our silver, we know the concentration is moles per liter, or if we know molarity, then it's going to be molarity times volume. And so we know that we had 150 milliliters of our solution with the silver, and that was 1 times 10 to the negative 3 molar. And then if we take that over our total volume, so here we're finding the number of moles, and we're going to take it over the total volume to get molarity. So our total volume was 150 milliliters from the silver, plus, I believe we had 200 milliliters of our sodium Na2S2O3. So 200 milliliters there. And that should give us 4.29 times 10 to the negative 4 molar. So that's our initial concentration of our silver. If we want to find the concentration initially of our complex ion, it's the same idea. We need to find the moles first. So we had, not 200. Let's just erase that real quick. So we had, okay. 200 milliliters of that, and it was a 5 molar solution, I believe. And then we've got the same total volume, so this looks like 350 milliliters. And if we divide there, we get 2.86 molarity. So pretty large molarity there. So the concentration of our complex ion is much bigger than the concentration of our silver. And our K1 and our K2 values are excuse me, both very large. So this means that both our formation reactions are going to go to completion. And the formation reactions are these right here. Okay, so let's look at our net reaction. If we take those two formation reactions and we put them together, we end up with silver plus 2 complex ions forms AgS2O3 And so we can do a before reaction and an after reaction. So we already calculated that we had 4.29 times 10 to the negative 4 molarity of our silver, and we calculated that we had 2.86 molar of our complex ion, and we don't have any of our product. So we're going to subtract, all the silver is going to react, so 4.29 times 10 to the negative 4 minus 4.29 times 10 to the negative 4 and plus 4.29 times 10 to the negative 4. And so that gives us an after reaction of essentially 0, and we'll come back to that in a second. If we take the 2.86, and actually this should be minus 2 of these because of the 2 up here, so minus 2 times 4.29 times 10 to the negative 4. Well, this is such a small value anyway that it comes out to approximately 2.86. Really haven't seen a change there. And then here we have our 4.29 times 10 to the negative 4. Okay, so this is our before and after reaction. Now, we said that both of these reactions would go to completion, so we want to find the concentration of all of our other ions. We basically found the concentration of our S2O3, and we found the concentration of our AgS2O3 too. But there is still some silver, and there is some of this intermediate species, this AgS2O3-. So we want to find the concentration of both of those. Well, if we look at our K2, and if you remember, let's go back to that reaction real quick. Okay, here's our K2. So this is our product, and here are our two reactants. We know this already, and we know this, so we can use the K2 value to solve for this one. So let's go back there. There we go. Okay, so our K2 is going to be our AgS2O3 over our reactants, one of which is the AgS2O3-, and the other one is our S2O3 2-. And that K2 value was equal to 3.9 times 10 to the negative 4. And so basically we can rearrange or just plug in. This one was 4.29 times 10 to the negative 4. And then we are solving for this, so I'll just put an X in there. And then our S2O3 was our 2.86. And so basically if we solve for X, we get that X equals 3.8 times 10 to the negative 9 molar. And so that's the concentration of our AgS2O3-. Okay, we also want to find the concentration of just our silver. So if we go back to our formation reactions, whoops. Okay, now we're looking at the first one. Here's the silver. We know the concentration of S2O3 2-. We just found the concentration of the AgS2O3-. Here's our K1 value. Okay, and so we know that K1 is equal to our AgS2O3-, because that's our product, and then on the bottom we have our Ag+, and our S2O3 2-. And that K1 value was 7.4 times 10 to the negative, I don't know why I keep wanting to say negative, I'm just used to it. Okay, that should be a positive, so we'll make that plus. And that's equal to what we solved for in the first part, so our 3.8 times 10 to the negative 9. Yeah, and I see this one should be positive too. Not used to them being positive. Silver is what we're solving for, and our S2O3 was our 2.86. And so if we solve for the Ag+, that gives us 1.8 times 10 to the negative 18. So very, very small. So here saying it was approximately 0 is really not that far off, but this is the actual concentration. And so what we see here is that our concentration of AgS2O3 2 3-, concentration is much larger than our AgS2O3 minus concentration. So here we had the 4.29 times 10 to the negative 4. This one was our 3.8 times 10 to the negative 9, which is then also much larger than our Ag plus concentration, which was our 1.8 times 10 to the negative 18. So that means our silver is the limiting, and the amount of S2O3 2 minus consumed is negligible because we start with such a large concentration to begin with. And so our assumption that both the reactions will occur is valid. Because all the Ag plus is essentially converted to our AgS2O3 2 3 minus, so that net reaction is valid. Okay, so let's look at how we use complex ions with solubility. So ionic solids that are nearly insoluble, we have to dissolve them somehow. We want to use them in reactions. And so once we precipitate out these qualitative analysis groups, we need to somehow be able to redissolve them into their separate ions. Some solids are more soluble in acidic solution. This won't work for chlorides, but it will work for others. And so we lower the concentration of the cation, the metal, through the formation of these complex ions, and this shifts the equilibrium to the left. So kind of just like we did in the example. And so, for example, if we have silver 1 chloride going to silver and chlorine, our KSP is 1.6 times 10 to the negative 10. We react our silver ion with some ammonia, and we get AgNH3+, giving us a K1 of 2.1 times 10 to the third, much larger, right, than our KSP. And then we take that and we react it with more complex ion, and we get an even larger K2 value. And so this is how we are lowering the concentration of the cation. So the silver will keep combining with the ammonia to form AgNH3 until the concentration of the silver and the concentration of chlorine is equal to the KSP value when you multiply them together. And so the concentration of the silver, the total concentration, you could just add them up from each of the steps. And so you could take the silver plus the silver with 1 complex ion plus the silver with 2 complex ions. And so we get silver chloride, this is our solid, right? This is what is insoluble, with some ammonia ion, and then we're basically splitting up the silver and the chlorine. Here the silver is bonded with the ammonia, but it's aqueous, so we could get our silver ion, and here we have the chlorine ion on its own. And if we wanted to find the K value, okay, we're going to take our two products divided by our reactant, and remember it's squared because of the 2 here, and we're not including the AgCl because it's a solid, and that's equal to KSP times the K1 times the K2, which is 2.8 times 10 to the negative 3. Now we can use this to calculate the solubility of solid silver chloride in a solution of ammonia. We will use X to represent the solubility of silver chloride, and so that's also the concentration of the chlorine ions, and it's the concentration of the AgNH3 2+. And so the concentration of the ammonia is our 10 minus 2x, the 2 because when you look at the balanced equation, we've got a 2 in front of the ammonia. And so our K value, which we know is 2.8 times 10 to the negative 3, is equal to x squared because these are on top, divided by the 10 minus 2x squared because of that 2 in the reaction. And so we get a molarity of 0.48, and so the solubility of silver chloride in NH3 is greater than the solubility in pure water, so we take the square root of the KSP. So there are 2 strategies for these water-insoluble ionic solids. If the anion of the solid is a strong or good base, then that means we can increase the solubility by acidifying the solution. If the anion is not a good base, then we dissolve the solid in a solution containing a ligand that forms stable complex ions with the cation. Just like we showed in the example, to break up the silver and the chlorine, we put it with ammonia, which is a complex ion or a ligand that will form a stable complex ion. Okay, and so we'll try a couple of problems with this and answer any questions you have in class. Have a good day.